Okay, so implicit functions theorem. That's this one. All right. So what does it say? We have a function f from an open set of R2s, function of two variables, of class ck. So I think you know what it means. Just means that it's a function that is continuous and its derivatives up to the order k are continuous. So at least with first partial order, first derivatives continuous. All right, that's what we need. And um, and we're going to look at the level line f of ab, f of xy is equal to 0. That's stated above, but if you're interested in f of xy is equal to some level value alpha, you can use auxiliary function g of xy, which is just equal to f of xy is minus alpha. And so that the 0 level line of g is equal to the alpha level line of f. Okay, so without loss of generality, we will be interested in level lines equal to 0. So let's say you have one set of data AB such that f of AB is equal to 0. We have one hypothesis to check, and that's this one, that the derivative in y of your function at point AB is not equal to 0. We will see why this is important. Well, for several reasons, but we will see why. Then what can we conclude? We can find, so here is how it goes. We can find some neighborhoods NA and NB around A and B. What does that mean? It just means that you are in the XY plane, that's A, that's B. Well, what you can find is small neighborhoods, that means small intervals around A and around B. Okay, so small intervals. That's going to be NA and NB. Small open intervals around A and B, such that you can find a function that goes from this interval around A and has values in that interval around B. Okay, that's what it does, such that you've got, if f of xy is equal to 0, that means y is equal to phi of x. Okay, f of xy is equal to 0, that means y is equal to phi of x. Another way of expressing that is to say that f of x, phi of x, is on your level line, is equal to 0. Okay, and so for all x in the neighborhood of A, we also have this relation. The first part here that was giving you existence of that implicit function, and this second part here gives you, well, a bit more information, although we may not be able to find its formula like what we did in the first example above about the circles. We may have more information. We will be able to find the slope of the tangent of that curve, so the phi prime of x, for all x's in that neighborhood. Okay, so we're going to do the proof of that theorem, or just outline the idea of the proof. And one thing that I want to be clear with is that don't learn these kind of formulas by heart. Well, you can, it's not that hard, but what is more important is to know to understand where it comes from. If you understand that this, you will remember it. Okay, you don't need to learn it by heart, especially if you don't understand where it comes from. So let's give some outline of the proof. Okay, outline of the proof of the implicit functions theorem. Okay, so what do we have? So we start with saying that, well, we are on that level curve, f of xy is equal to 0. What does that mean? What does that mean in terms of Taylor expansion? So let's take the Taylor expansion around my points A, B, and first order. What do we have? we have that f of xy close to a and b are going to be f of ab plus, so we get the sum of the first order partial differentials times the increase in each direction. So that's going to be x minus a times df over dx at point xy plus, so sorry, same stuff in the other direction. So that's going to be x minus b times df over dy at point xy. Sorry, at point AB. Oh, both should be in AB. Okay, plus some small o of, so the norm of x minus a, y minus b. Okay, so that means that if we are on that level curve, we have more specifically that this is equal to 0 and that is equal to 0. So that part should be very close to 0 because, well, the remainder, the small o, is supposed to be negligible compared to what's coming previously. Okay, so let's try this. What do we get? Let's just write, we have x minus a times df over dx at point AB plus x minus b times df over dy at point AB is equal to 0. Is approximately, well, that's not a straight equality, that's an approximation. So, well, sorry, that's a y. Sorry about this. So, well, it's very clear that we can get the y out of this equation. So what do we get? We get that the y, as I remind you, I'm looking for y as a function of x, is going to be given by, well, I'm just solving this equation with respect to y, so I get b minus x minus a times df over dx at point AB, and I should divide that by df over dy at point AB. Okay, so what do we have here? So this is, again, that's not an equality, that's an approximation, and that's why this is not really a rigorous proof. But what does this look like? This indeed actually looks like a first order Taylor expansion for the function, well, y is equal to phi of x, which we are looking for. Okay, why? Because we get that's phi of x, that's phi of a, because of course if I find the function such that f of x, phi of x is on my level curve, so is equal to 0, that means when x, the first requirement of course is that for a, b, we know that it's equal to 0, so we know that phi of a is actually equal to b. Okay, so that looks like phi of x is approximately equal to phi of a minus x minus a, which is just the increase between x and a, times something. And that something, according to first order Taylor expansion, that is just the first order derivative. That should be phi prime at point, well, a. Okay, well, don't forget we have a minus here. Okay, so we get that phi prime of a should be equal to minus df over dx at point AB divided by df over dy at point AB. Okay, and now you see that we really had, so that's the formula we have in the end, but that's the one that you see. If you know how to get it back, it takes 2 seconds. So maybe you should now pause the video and try to rebuild that formula, okay, from the first order expansion of my function f of xy around AB. Okay. Okay, so you will tell me maybe that's very nice that we found out how to find an expression for phi prime of a, but if you look at what's given as a formula, it's phi prime of x. So let's show that it's also going to stand for phi prime of x. So phi prime of x, do we have a similar formula, except that instead of a and b, I have x phi of x. All right, so let's say we start with this same idea. F of x phi of x is equal to 0. All right, so what's happening if so the idea is that I have constant value. So if I do the derivative according to x of this function, as we are keeping by definition on the same level line, that should be 0 because we are constant, okay? X phi of x is a constant value, right? So let's write that this derivative is equal to 0. This derivative is equal to 0 just because, and this is also what we got from the Taylor expansion, where the term of f of x y was equal to 0 and f of ab was equal to 0. That's just the same idea. Right, so we write that derivative, so now you know really well how it works. It's going to be dx over dx, that's 1, times df over dx plus d phi over dx times df over dy. Okay, that's again all the chain rules that we've been working on many times. Right, so what do we get? We get what time df over dx applied to x phi of x plus df over d phi over dx, that's just going to be phi prime of x, times df over dy. So note that this was the derivative according to the second variable. Okay, that's one. Df over dy, again, applied to the point x phi of x. And then that should be equal to 0. Okay, and again, we can do the same kind of thing. We can extract, if I'm looking for phi prime, we can extract phi prime out of this equation. It's going to be minus df over dx at point x phi of x divided by df over dy at point x phi of x. Okay, and so again, we need that this is the bottom of that fraction is different from 0. If we go back to our circle example above, what is that restriction corresponding to? It corresponds to these points. Okay, you see at that point I have that the derivative in y is going to be equal to 0. Okay, so that I would of course not be able to make to express this kind of thing as a curve, not a curve that can be written as as y is equal to phi of x, okay, because that's not defining a correct function. Okay, but you can find you can use it the other way around. You could put x is equal to psi of y. Okay, indeed, if that's x and y, you can describe this. Sorry, I used the same color, but you can really describe this part of a curve as a curve giving you x as a function of y, even if you couldn't do the contrary. Okay, so then you would have something like f of psi of y is equal to your level line, to 0 in our case. Okay, all right.